and welcome to part 2 of this series of lectures on special relativity. Today, we're going to be going over what we did last lesson, which you can find on the IAA's YouTube page, and then we're going to launch into a discussion of space-time diagrams, like the one that you see over here, and we'll learn how to interpret these. And then we'll also discuss Lorentz transformations. So let's look at what we did last time. In our first lesson, we discussed the use of reference frames, which are essentially just points of view, but using more fancy language, that's more physics related. So, for example, a reference frame might be you sitting on the ground right now, or it could be someone in the International Space Station, someone traveling in a car, and so on. And a reference frame is called an inertial reference frame if it's moving at constant velocity, which means that it's not turning, it's just moving in the same direction without any acceleration or anything like that. So we're going to be considering inertial reference frames most of the time when we're doing special relativity. When we consider non-inertial reference frames and acceleration, things get slightly more hairy, and we might get to that in a future lesson. However, right now, just like before, we're only going to be considering inertial reference frames. So in this picture on the top left of the slide, we can see a man with a flashlight. And one of the things that we discussed last time about this image is that whenever you have, say, a ball, and you're throwing a ball towards someone, if you're moving, say, 10 miles an hour, and you throw the ball is going to be moving 10 miles an hour faster than if you just stood still on the ground and threw it. However, as we discussed last time, Einstein suggested that the same was not true for light, and that light has a constant speed regardless of your reference frame. So if, as we see here, the flashlight is moving, the light from the flashlight still moves at the same speed. If the flashlight is moving backward, it still moves at the same speed. If the flashlight is moving and the observer is moving, light still moves at the same speed for everyone, which is a really weird concept. But this, as we saw last time, is integral to our idea of special relativity. The next thing we discussed was measuring distances. So on the top right, you can see a very simple triangle with 3 sides, and, well, a right triangle, mind you, and that we can just use the Pythagorean theorem to find the distance from, say, one of the points to the other, using the handy formula a squared plus b squared equals c squared. Or, if this was in 2 dimensions, it would be something like d squared, where d is the distance, equals x squared plus y squared. So we scaled this up to working within not just 3, but 4 dimensions, as seen by this 4 position here, where a 4 position is just a 3 position, aka its real-world coordinates in x, y, and z, length, width, and height, but then we also add on a nice little t component for the time. And obviously we can't see that axis, because our world is strictly 3-dimensional, so we just envision there being a 4th coordinate for t. And using that, we come up with a slightly different metric for distance, which is known as delta s, as you can see down here, or we prefer to call it the space-time interval, where the s comes from the word space-time. So the space-time interval squared equals c times delta t squared, which is essentially the distance that light takes to travel to that point in time from the origin, which is time equals 0, minus the change in x squared minus the change in y squared minus the change in z squared. So it's slightly different from the Pythagorean theorem, but overall it's the exact same concept, just measuring distance in a different coordinate system. Alright, so now we're just going to do a little bit of practice using invariance of the interval, which is, again, an exercise that we did last time, so you should be fairly familiar with this by now. So one of the things that Einstein also suggested was that in special relativity, the space-time interval between 2 events is going to be exactly the same. So again, the 2-dimensional analog of this in our real world right now would be that distances, regardless of where you are and how fast you're moving, etc., are the same. However, as we'll see, distances are not the same in special relativity, but the space-time interval, again, as Einstein suggested, is. So let's use this in an example. So let's say that we have the Earth and a rocket ship. And let's say I am standing on the Earth, and we have something called a light clock. So a light clock is this lovely little device that has two mirrors, one stacked on top of the other, and light beams from the bottom from one of them up to the other and back down and continues to oscillate. So let's assume that for our purposes, the beam of light goes up and down, and that's it. So it just has one little up-down interval. So let's also assume that our vertical distance, the height of the light clock, so to speak, is 3 meters. So if we go ahead and plug this into our handy formula at the top right for our interval, we see that the space-time interval in the Earth frame is, well, we know that there's no motion in the x, y, or z axes because we're assuming that the Earth is staying stationary, as are we on it. And since we're moving up and down, we have to multiply this distance by 2. And when we square it and then take the square root of that, we get that the space-time interval for this action on Earth is equal to 6 meters. Now, let's examine this in the rocket ship frame. So, on board the rocket, let's say the rocket has moved a total of 2 times 4, which is 8 meters. So, that means that if the height of the light clock, which stays the same, is 3 meters, but the rocket has moved, let's say, 4 meters each time the light clock goes from one to the other, that makes this CT guy over here equal to the Pythagorean theorem used on 3 and 4 as the side lengths, which is 5 meters. So 5, that means the light has moved 10 meters in the rocket ship frame. But on Earth, the light has only moved 6 meters, which is really weird. So if we plug that in to our interval formula for the rocket, and then subtract from that the distance that the rocket has moved in our little delta x term, and that is going to be, well, the rocket's moved 4 meters each time the light bounces from bottom to top, so that means that the rocket's moved 8 meters, and again, this simplifies to 2 times 5, which is 10, so then we get 100 square meters minus 64 square meters, that's 36 meters squared, and if we take the square root of that, we get the space-time interval for the rocket frame is 6 meters as well. So, what does this mean? Well, first off, the Earth and rocket ship are in 2 completely different reference frames. The rocket ship is moving, the Earth is not, the Earth is presumably at a different place than the rocket ship, and so on. Likewise, light travels different distances in each frame. In the Earth frame, light travels 6 meters, in the rocket ship frame, light travels 10 meters. And the light also takes a different amount of time to travel. In the Earth frame, light takes 6 meters divided by c seconds to travel, but in the rocket ship frame, it takes 10 meters divided by c seconds to travel. However, as shown by our calculations of the space-time interval, both frames observe the exact same space-time interval between when the light first started from the bottom and then once it hits the bottom once again. So take some time to think about this and see how crazy it is. And with that, let's move on to something slightly different that we haven't talked about yet. And this is called a space-time diagram. So let's say that we have this little green point, ball, grass, whatever it may be, moving along our x-axis, as represented by this pink pair of axes here. And since it's only moving on the x-axis, it can either move this way or this way. And let's say that it carves out some little path, so it does something like this. And if it does, we can look at the position of the ball, let's call it a ball for now, as it changes over time. And that is exactly what a space-time diagram is. So, a space-time diagram measures the position of an object. Here, it's a 2-dimensional space-time diagram, so it's measuring the position on x, its position in time on t. But then we multiply that by c. Why do we multiply this by c, you might be asking? Well, remember, c is the speed of light, which is a universal constant, and b is a speed. And a speed times the time also becomes a distance. So that way we get a distance in x versus distance in terms of ct. So here's another handy little thing we can do with it. Let's be weird and set c equals to 1. Now obviously c is not 1. C is 3 times 10 to the 8th meters per second squared. But let's pretend that c is just 1 and that it's unitless. So then we get the velocity of this object along in the space-time diagram is just going to be the slope of the line, of the tangent line, to its space-time curve, which is represented by this funny-looking green thing. So another thing to note is that when the speed of an object equals the speed of light, then we'll call it the v-rel, which means relativistic. Speed here equals 1. And that is represented by this yellow line, which, as you can see, has slope 1. So when x is 1, then ct is also equal to 1 because c is 1, and so on. Oops. Alright, so now let's get into something a bit more interesting. So the first thing to note is that our space-time diagrams, as seen on the board, are only working in 2 directions, x and t. We don't have a y dimension, and we don't have a z dimension. So in our space-time interval formula, represented right here, we can take out the y squared and z squared terms. But also remember that c equals 1 now, so we can take out c as well. And thus we get that delta s squared, which is our space-time interval squared, equals delta t squared minus delta x squared. And that's it. That's our 2-dimensional space-time interval formula. Okay, you might be wondering, so what does this tell us? Well, let's set the space-time interval equal to some number. 0, 1, 2, 3, and so on, whatever you'd like it to be. And let's graph the resulting curves that occur. So when we do that, so some constant squared, or some constant, equals delta t squared minus delta x squared, is actually the shape of a parabola, which is exactly what you can see in the curves right here. And because this means that our interval is invariant, the parabolas associated with a specific space-time interval are known as invariant parabolas. Additionally, we can look at the cosmic speed limit from this graph as well. So if you look at all of the invariant parabolas right here, you'll notice that none of them ever cross the line v equals c, represented by the pairs of red lines crossing the graph. They only inch up to it very, very, very slowly, but never touch it, and again, never cross it. This is a really easy visual way to see that the slope of anything along these invariant parabolas cannot be greater than or even equal to c. And thus that makes c, or the speed of light, our cosmic speed limit. So that's a useful way to notice something which isn't always inherently obvious. Alright, so now that we've gotten a straightforward introduction to space-time diagrams, let's discuss something slightly different, going back to classical Newtonian and Galilean mechanics. So let's say that we have 2 observers, right? Let's say we have this guy right here standing on Earth, and then this other guy, let's say B, standing in the rocket ship. And let's say that they both observe some event O. Let's say that O is, I don't know, like right over here. However, B, the guy in the rocket ship, is moving relative to the guy standing on the ground, and is moving at some speed v along the x-axis, which is going to be right and left in our case. So no up and down motion, no into or out of the page motion, just moving right and left. So let's say that observer A on the ground sees event O occur at some x position and some time, right? So our question is, when does B see this event? And again, we are only considering this in Newtonian mechanics. No relativistic effects, light, speed is not a constant, and so on and so forth. And we're also going to consider this in an inertial reference frame, which, if you'll remember from the beginning of the video, means that our speed is constant for v. It's not accelerating nor negatively accelerating. So let's take a look at some graphs. Now, we can just graph some simple x versus t graphs, which are sort of like space-time diagrams, but because here c isn't a constant, it's not exactly a space-time diagram. It's basically just a position versus time diagram. So obviously here we have our position and time for A, and A observes O right here at some x naught and then t naught. But then B is just moving faster than A. So B could technically be here, 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 and then keeps moving on to the right. But that doesn't affect at what time B observes event O in Newtonian mechanics. It just affects the position, right? So let's say as B moves further in the plus x direction, as seen by this little pink line here, the distance at which it observes O from its origin decreases in terms of x, but the time is still the same. And eventually, if B is right on top of O the moment it observes it, then that distance is just 0. So that's very simple. But the time is still the same. So it's simple to see that in Newtonian physics, all observers see the same time for an observation. But they can see the events at different positions depending on their position relative to the other, and also depending on their speed. And we can combine that into saying that they can see events at different positions relative to their inertial reference frames. And using that, we get the 4 equations at the bottom. So let's assume that we are only moving, once again, in the x direction. No motion in y, no motion in z. And we got the following equation. So where the primes are used for B's location for O. So we get x prime, which is the x location for B of O, equals x, which is the location of O for A, minus vt, where v is the speed of B, and t is the time that it's observed for A. And likewise, we can see that, well, the y position and z position are going to be exactly the same. Why is that? Because we aren't moving in the y or z direction. We're only moving back and forth in the x direction relative to A. And also, as you can see in the last line, the time observed for B for O is the exact same time observed for A. So, let's now do the exact same scenario, but instead, let's assume relativistic physics. And to simplify things, which will complicate things, but to simplify things just a little bit more to help us out, let's also assume that event O occurs at the origin of A's reference frame. So if we look back at this graph, completely disregarding B, let's say that O occurs right here at x equals 0 and t equals 0. So what happens in this instance? Well, let's use our space-time interval formula, using c equals 1 in only the x and t dimensions, which is delta s squared is delta t squared minus delta x squared. Next, remember, Einstein said that the interval is always invariant in these two reference frames. So the interval for A for O is the same as the interval for B looking at O. So once again, or actually, let's say that this doesn't necessarily occur at the origin, but it occurs at A's x-axis origin. So that means that our delta x squared A term completely drops out, because if it occurs at the origin, well then delta x is 0. So then we just have delta t A squared equals delta t B squared minus delta x B squared. And we can complicate this just a little bit. So we notice a factor of delta t B squared can be taken out of the right-hand side of the equation. And we can make that right-hand side equal to delta tb squared of 1 minus delta xb squared divided by delta tb squared. But, oh, hey, we've seen this equation before. So, remember, the relativistic velocity as we've defined it is delta x divided by delta t. So if we skip forward a little bit, and we see that exact expression right here, but squared. So delta t a squared is thus equal to delta t b squared times 1 minus v squared relativistic speed of b. Now, we can divide both sides by this expression, take the square root, and we get that the change in time for observing O for B is the change in time for A divided by the square root of 1 minus the relativistic speed of B, where the relativistic speed of B here is just going to be this expression, delta x divided by c delta t, but here we're setting c to 1, that's delta x over delta t. And we can do something very similar for calculating the x position of O for B, and then we get that that's the relativistic speed multiplied by the change in time for A divided by the square root of 1 minus v rel b squared. Okay, so that helps us a little bit, but we're not done yet. So firstly, we see a clunky term occurring in the bottom of both expressions. This 1 over the square root of 1 minus the relativistic speed squared. And that we can define to be a constant, because in physics, whenever we have a weird clunky expression, it's always nice to define that as a constant. And let's call that constant gamma. So gamma here equals 1 divided by the square root of 1 minus the relativistic speed of b squared. Then, let's also suggest that the transformation between both reference frames is linear, since that's what it is in the Galilean physics. And again, if we do a little bit of math finagling, which I won't go into great detail here, but you can take a look at the link in the video, and which will be put in the description, we get the Lorentz transformation equations. So, let's take a look at what these are. Well, here we have x prime equals gamma, which is our lovely little constant in the bottom left, times x minus vt. Note the difference here between this and the Galilean transformation, which does not have this gamma, and is just x minus vt. So we get the same things for the y and z terms, because once again, we simply aren't moving in the y and z directions. And the t term now is also slightly complicated. So we get t prime, which is t for b frame, equals gamma times t, which is t for a frame, minus vx over c squared. But then again, the c squared is just 1, so we can drop those out. And again, note how different that is from in the Galilean and Newtonian view, where the times are equal. So here, as you can see, the times are most definitely not equal because of our gamma term and also this vx over c squared. So, what on earth does all of this mean? Well, let's take a look at some space-time diagrams one more time. So, the Lorentz transformation equations basically suggest that, once again, the interval is invariant in both reference frames. But because here, B, which will also represent by the prime frame, is moving, its x and ct axes will be angled. So it's sort of like smushed relative to the x and ct axes for our non-moving A reference frame, we can call it. So they're also smushed relative to the line x equals t with slope 1, because again, that's our cosmic speed limit. And they're smushed with an angle alpha, whose tangent is equal to v over c, where v is just the speed of the object, and v over c, we'll call that a constant beta, because again, it's a nice expression that will be handy in our further relativistic adventures. So let's do a really quick comparison right here. So in A, we have our stationary reference frame, which we'll call S, we can call it A, we can call it whatever, and then our S prime frame, or the prime frame, which is the moving one. Then, due to the Lorentz transformation equations for the prime frame, when we look at the prime frame from the non-moving frame, the prime frame is smushed in the non-moving frame's reference point. for an angle beta, theta, alpha. They're exactly the same thing for us here. And also note that, once again, the distance between the origin and the event, whatever the event may be, it could be r, it could be q, it could be p. Here again, it could be r, it could be q, it could be p. The interval between those events is going to be the same regardless of your reference frame. However, the distance and the time might be different, but the space-time interval is always invariant between all reference frames. So let's take a look at some weird things that we can do with these. The first thing to notice is, one, how cool space-time diagrams look in comparison to normal Euclidean space. So here is Euclidean space, where we have, and these circles represent x squared plus y squared equals some constant. We could call those, say, invariant circles. And they're just normal circles. And here, the x prime and y prime frames are represented by a simple rotation of the axes. However, if we take a look at our relativistic spacetime diagram on the right, instead of getting invariant circles, we get invariant parabolas, which 1, sound longer, cool, 2, have cooler colors, that you can see here, and 3 are just also slightly more unique. We also have a sort of cosmic speed limit for those parabolas and for any objects, as defined by the line v equals c. And when we get a weird sort of rotation, it's actually going to be a smushing of the curves about v equals c, rather than just a mere rotation. So, all in all, spacetime diagrams are a lot more fun than just regular Euclidean space. Here's another fun thing that we can do. So remember that v equals c is our cosmic speed limit? Well, if we're just moving at speed 0, then our x never changes. So we just move up and down the ct axis. As our speed increases, we get closer and closer and closer and closer to moving at v equals c, but we can never go past it because, once again, as defined by our invariant parabolas, the speed limit of the universe is v equals c. So, using this, we can determine some really cool things. If we look at our space-time diagram here or here, either way, the future of whatever events are to come is represented by the area between the two v equals c and v equals negative c lines and the upward part of them. The past is everything at the bottom, because that's where we get negative time. However, since going into this region or this region would require us moving at a speed greater than c, those areas of our graph are undefined, meaning that we can never, ever, ever go into those regions. So the only two parts of space that we can, of 4D space that we can ever really observe are stuck within this little hourglass shape. And also, don't forget, right now we're just working in 2 dimensions, x and t. What if we scale this up to 3 dimensions? So now we're moving within the hypersurface of the present, which is just a fancy way of saying that we're moving in a 2-dimensional plane, x and y. But while we're moving in that 2D plane, time is slowly progressing. So that basically makes it from just having 2 stacked triangles to having 2 stacked cones. So instead of just having a future triangle and a past triangle, we now have a future light cone and a past light cone. Because, once again, we can move in 2 dimensions, so that, and since here we're moving in 1 dimension, that means we have a 2-dimensional future and past. Here we have a 3-dimensional future and past. And once again, we can only stay within those 2 cones in our universe. It's impossible for us to go outside of them as defined by relativity, because that would require speeds of v greater than c. Alright, so today we've found basically 2 very helpful tools. One of which are the Lorentz transformation equations on the top right, and the second of which are space-time diagrams, invariant parabolas, the interval, and everything associated with them. Using just these 2 simple things, along with invariance of the interval and Einstein's postulates, you can solve almost any special relativistic scenario. You can factor things in like acceleration, you can do it for inertial reference frames, and so on and so forth, albeit, of course, with more mathematical complexities, but these are your essentials for your relativistic toolkit. So, I hope that was helpful, and next time we'll end up applying some of these to some fun relativistic paradoxes. And on the bottom left is a teaser for the next video, and I look forward to seeing what your guesses are for which paradox we'll be doing next time. Take care, everyone, stay safe, and see you for part 3.